concentrations will affect the rate of that reaction. So let's take a look at what that looks like and what this can mean for us. So concentration and rate laws. How do we determine what effect the concentration is going to have for the rate of that reaction? Well, we keep every concentration constant except for one reactant and see what happens to the rate. So since we've controlled everything else, the only change we've made is in one concentration. So any change that we observe in the rate is due to that species changing rate or changing concentration. So experiments 1 through 3 show how the concentration of the NH4 plus affects the rate of this reaction. Okay? But experiments 4 through 6 show how the NO2 minus change affects this rate. Okay? And what this gives us, once we've been able to analyze what effect each concentration has, we can write something called a rate law, which shows the relationship between rate and concentration for all reactants. Okay? So the general form of the rate law is rate is equal to K times A to the X, B to the Y, where X plus Y is equal to the reaction order. So there'll be an order for each reactant. We'll talk about how to find those. There'll be a rate constant, which is this K. And for this particular rate, we know that this one is K times NH4 plus times NO2 minus. Now, I'll tell you how we got to that in a little bit. But that's the general form of our rate law. Well, that's cool, right? That should be easy. Now, we're going to compare lines 1 and 2. We doubled the concentration of NH4 plus, but we keep the NO2 minus the same. And so we have a 0.020 over 0.010. And that's equal to the rate for that concentration of 0.02, 10.8 times 10 to the minus 7th. And that's over the 0.01. And that's 5.4 times 10 to the minus 7th. If I double the concentration, the rate doubles. That's awesome. That's directly proportional. It's a 1-to-1 ratio going up. So that order is 1. Okay. If we compare lines 4 and 5, we double the concentration of NO2 minus and keep the NH4 plus the same. So now we have the 0.0404 over 0.0202, and we look at the 21.6 times 10 to the minus 7th over 10.8 times 10 to the minus 7th. That is, again, double the concentration, the rate doubles. So directly proportional, as one goes up, the other goes up directly, same relationship. That's an order of 1 as well. If the concentration doubles and the rate goes up by 4, that's a second order. Okay, and we'll talk about what those orders are and what they mean a little bit later. If the concentration doubles and the rate does not change, which happens, then the order for that component is 0. So it's not a part of the rate law. So once we know the order of each component, we can add them to get the overall order. So in this case, the order of the first one is 1. The order of the NH4 plus is 1. So the overall order is 2. Okay, that's what we're talking about there. Go awesome. Let's do some practice with that. So I've given you 3 reactions here and some data for each of them. And we're going to determine what the order is with respect to each of these concentrations that we're looking at. So in this first experiment, we have cisplatin reacts with H2O to give us this complex product, okay, which is an ion. So we're going to look at what happens when we change that concentration. So if I change my concentration, and I have this row right here, so I'm going to look at the 0.012, which is the second row, over the 0.006. And of course, I didn't leave myself enough space, so I'm going to write the rates down here. 1.8 times 10 to the minus 5th, and 9.0 times 10 to the minus 6th. Okay, so I'm going to do my division. So I have 0.012 divided by 0.06, and that gives me a factor of 2. And then this other side, 1.8 times 10 to the minus 5th divided by 9.0 times 10 to the minus 6th. That also gives me 2. So the exponent on that, what we're looking for, is this exponent right here, and that exponent has to be 1. That means that that exponent is 1, so that's a first order. So this is first order. Cool, awesome. Now I can do that math with the next set. Okay, we can do this one too. And I'm going to pull this. I'm actually going to put this one up here at the top. So I take the second row, 0.015 over the 0.0. Solving for that exponent, the x. So that's equal to 2.4 times 10 to the minus 8th over 1.6 times 10 to the minus 8th. 1.6. Okay. So happy math there, 0.015 divided by 0.01. That gives me 1.5. And that's raised to some exponent. And we have our 2.4 times 10 to the minus 8th divided by 1.6 times 10 to the minus 8th. And that is also 1.5. And so since 1.5 is 1.5, it's also first order. Go awesome. So it's not always a nice answer that we get, like, it's not always 2, some nice even number. We can get weird things. We just need to know what the relationship between those two numbers are. Let's talk about this last one. So in the second row, we have 0.0075. We're going to put that over the first row, 0.05. And that's got some exponent to it. We have our second row's rate times the 7th divided by the first row's rate, 1.10 times 10 to the minus 5th. Nope, that's not 5th, that's 7th. That is a 7th. And we see what that looks like. So 0.0075, 0.05. And again, that gives me 1.5. And 1.65 times 10 to the minus 7th divided by 1.10 times 10 to the 7th. And that also gives me 1.5. So look at that. All of these are first order. Oh, isn't that exciting? But that's how we do that math. Okay. Let's talk about what's next. So do we have any questions on how we do that math so far? We're always going to do the exact same thing. So different rows, we have the concentration and the rate, concentration and the rate, find out what the ratios are, and see what exponent we need to raise that to that concentration to make sure that we get that relationship. Now we've talked quite a bit about first order reactions. We found a bunch of them that were first order. In that case, rate depends on the reaction concentration raised to the first power. We can use any of the following equations to solve for A initially if we know what it is at a certain time. A at a certain time if we know what it is initially and the time, or we can solve for the rate constant K. So we have this series of equations that applies for first order reactions. Now, we're going to have a similar set of equations for our zero order reactions and our second order reactions. But these are the ones that apply for first order reactions. So of course, rate is equal to negative the changing concentration of A over time. Rate is equal to K times the concentration of A. We can use the natural log of A at any time, the concentration of A at any time over A initially is equal to minus KT. And the natural log of A is equal to minus KT plus the natural log of A0, so the initial concentration. We can also use the equation below if the reactions are in gas phase, so it's similar. Instead of concentration, we're talking about pressures. We can use this equation to find the half-life. So a half-life, this is the expression for it, 2.5 equals 0.693 or K. A half-life represents how long it takes for half of the material that is present to decompose, to go away, to disappear. Okay, and we can plot all of this data, and we see that the natural log of the concentration versus time is a straight line. So if we plot concentration versus time, that's not a straight line. The natural log of concentration versus time is. This intercepts the y-axis at the natural log of the initial concentration, A0, and the slope is negative K. Okay, so we can find that K by looking at one of these plots. So that's everything I have to say about those. Now, will you find these equations on your test? Yes, you will. You will find that there are blocks in exam handouts. And this is in the useful equations on page 6. You'll find that there are boxes for each of these that we're going to talk about, but they are not labeled. So I'm not going to tell you which set goes with which order. You're going to need to know which set goes with which order. And then the equations will be there for you to use and work with as you need. Okay, so that's how that's going to work. Second order reactions. So the rate depends on the reaction concentration raised to the second power, or the concentration of two reactions both raised to the first power. You can use the following equations. Okay, rate is equal to negative A over concentration of over change in time is equal to rate is equal to K times A squared. And in this case, we're looking at 1 over the concentration of A at time t is equal to KT plus 1 over the concentration of A at time 0. Okay, so same kind of deal that we talked about before. Here, my T1 half is 1 over the concentration of A0 and times K. So it's 1 over K and 1 over A concentration of A at time 0. And finally, we can plot this. And again, because we're looking at 1 over this concentration, the plot of that 1 over is going to, versus time is going to be linear. Notice that this has a different slope. So our slope is equal to K, not negative K. And this intercept again is 1 over the initial concentration of that particular species. So those are our second order reactions. Okay, so 1 over is second order, natural log is first order. Move on. Now we're going to talk about something called pseudo. So let's look at this. Rate equals K times A times B. Now this can be a hard thing to measure and treat mathematically. Usually we run this changing one concentration while having the other one be a really, really large concentration. And what happens is if one of those is a really, really huge concentration, it effectively becomes part of the rate. We won't see any changes from that. So we can look at the effect of the other concentration because this second one is so large. And so we call that a pseudo order first reaction. Pseudo first order reaction. Sorry, I got it in the wrong order. And what that means is that we're only looking at the effect from one of those concentrations and not both of them. So it appears to behave like a first order reaction. Okay? So that's what that refers to. And now let's talk about zero order reactions. So the rate does not depend on the concentration. I don't care how much I have. It does not change. That rate is constant. And so that rate is equal to K times the initial concentration. And the concentration at any given time is equal to negative K times T plus the concentration at time 0. Our T1 half, our time for half of it to disappear, is equal to the concentration of A at time 0 over 2 times K. And if we plot this, what we see is that the concentration of A versus T is linear because that rate has nothing to do with the concentration, so it's going to go down at a constant rate. And the slope of that line is negative K. We hit the intercept is at the initial concentration, A0. Okay, so that's how that works. So let me recap that. The natural log is for first. That's the nature of that equation. The 1 over the concentration is for second order, and the concentration versus time is 0. Okay, so that's what we're talking about there. Isn't that fun? So we can collect all of that information. This is just meant to be a useful thing for you to look at, right? So if we look at the differential rate laws, we have 0 order, change in concentration over change in time. Okay. This one, first order, change in concentration over change in time gives K times the concentration of A. Second order gives me K times the concentration of A squared. So if we were to plot concentration versus time, we end up with this one looking like this one looking like this, and this one looking like this. That's not very helpful. we know that the integrated rate laws look like this. So our zero order does not do anything to that concentration. It's just the concentration that we're considering. Our second order is the natural log, or sorry, our first order, next one. And our second order is 1 over concentration. So again, straight line determining plot is going to be what we just talked about. So for our zero order, it's concentration versus time. For our first order, it's natural log versus time. And for the second order is going to be 1 over the concentration versus time. And you'll see that for the zero order, the slope is negative k. For first order, the slope is negative k. For second order, slope is equal to k. The relative rate versus concentration. Okay, so when we talk about no effect, we see that concentration of A being 1 gives me a rate of 1. Concentration of A being 2 gives me a rate of 1. Concentration of A being 3 gives me a rate of 1. So there's no effect from that species. We have a concentration of 1 and a rate of 1 for our first order. Concentration of 2 gives a rate of 2, and a concentration of 3 gives a rate of 3. So direct proportionality there. For our second order, concentration of 1 gives a rate of 1. Concentration of 2 gives a rate of 4. And concentration of 3 gives a rate of 9. So that concentration squared. And then we have our half-life equation, okay? Each of which is given in the list that you have, okay? So that's just a collection of that information. This may be helpful to you when you're working on some of the things that we're going to be doing with this. You will not get that on the test. So let's do some practice. Based on this image, would I expect the order of N2O5 to be first, second, or 0? Well, okay, let's take a look at what we're looking at. So I have the concentration of N2O5 versus time. So this would be the zero order one. Here I have the concentration of the natural log versus time. So this is first order. And this one is the 1 over the concentration of N2O5 versus time. So this would be my second order. Now I'm looking for the one that's linear. And this is the only one that makes a line. So I know that this is first order because that is the plot that is linear. Okay. And we can do this with all of our data. We can take our data, plot each one of these, see which one is linear, and that's the one the order that we're talking about. Okay. Let's try this again. Based on what you see in these graphs, would you expect the order of NO2 to be first, second, or 0? Well, again, we've plotted our data, and we've done them in the same order as we did before. So this is 0, this is 1, this is 2. And notice we've plotted the data, and then we've got a line of best fit. So you see a straight line here. That's our line of best fit. And for this one, not a very good match. For this one, it's a better match, but it's not a good match. And for this one, it is a match because this is linear. So we would expect that this one will be second order. Okay, so NO2 is second order there. Okay, awesome. That's fun. Questions about that? Hold on just a second. So ways that we can determine order. So we can use the types of ratios above to determine order for each reaction using initial rate data. We can plot the data over time using the forms that we've talked about. So concentration versus time, natural log concentration versus time, and 1 over concentration versus time. Whichever one is linear, that's the order. For each reaction, only one of those graphs is linear. So that's the one that is the order that you need. Once you know those orders, you can determine a concentration at a specific time, a half-life, and the rate constant using the integrated rate laws that will be provided to you. Okay. Rate constant is either slope or the negative slope of the linear plot, depending on which one we're talking about. Concentration time equations are provided for each order, and the half-life is defined by the order of the reactions. It will tell you which equation to use. Now, all of the calculations that we're talking about here are valid on exams, and these equations are provided to you. They're not labeled, so you need to know what each represents. There's practice for this, and make sure that you've taken a look at it because I've tried to ask you some of each of these questions to give you an idea what they look like. And here's a summary of our rate equation. So, zero order, rate equals K. Concentration of A at time t is equal to the negative K times T plus the initial concentration. Half-life is given by the initial concentration divided by 2 times K. First order, rate equals K times the first times concentration of A. Our concentration time equation is the natural log of concentration at time t over the concentration initially equal to negative K times T, and our half-life is 0.0 or 0.693 over K. Our second order, the rate is equal to K times A squared. 1 over the concentration at time t is equal to K times T plus 1 over the concentration initially. Our half-life is given by 1 over K times that initial concentration. Okay, so that's my summary. So if I were studying, I would keep this around and I would keep my exam equations, because as I look at this, I can say, okay, it's this order, it's that equation, then I can find it over there, and I'll learn to associate which order is which set by where it is. Okay, that's what I would do. So questions, comments, problems on that? Okay, I'm going to go ahead and I'm going to go ahead and pause here, and I'll be back in just a minute. Thanks, guys.